Okay, hello everyone. Thank you for tuning in. I'm Laurie here at the Engineer Cafe, and I'm here with Chin to do some programming in parallel algorithms, GPU coding, and a lot of other fun stuff. I don't actually know much about this topic, so I'm going to be learning a lot along with everyone else, but I'm really happy to have someone experienced here doing the actual talk and the content. So, can you tell us a little bit about yourself and
Okay.
how you've come into doing parallel programming like this?
Okay. Hello, everyone. My name is Chin, and I'm a programmer working. Have some experience with C and C++ before, and my last job is on a chemical company with with machine learning techniques. So we work a little bit on the GPU, and I'm very happy today to share some experience and some examples with you guys. Okay.
Great. Should we get right to it? Should we take a look at your slides and your presentation?
Okay, let's work on. Okay, let's start. So today's topic, we are going to go through an introduction on parallel programming on GPU with a lot of examples. Okay.
Maybe,
Yeah.
maybe I'm interrupting.
No problem.
Can you explain a bit about what exactly you mean by parallel programming?
Parallel programming. Parallel programming means you are working on new hardware. It could be GPU. It could be also on CPU with more cores. For example, right now we have 8-core always multi-core CPUs, so it could be a parallel programming too.
Awesome, thanks. Yeah, okay, sorry to interrupt like that.
No problem. Okay. So let's move on. Before we start, there's some there's some materials. We have event page from Engineering Cafe. Thanks for organizing this event. And there is a event page in.
I link to it in the YouTube video. So if you're watching the stream on YouTube, just go to the description and click on that link.
Yeah, I will show it a little bit here. So we have the event page here. There are some material you need to prepare. We have a data link. We are going to use molecules from a database, and I will also give the code, share the code here too. So you have all the links here for the coding section.
Awesome.
Okay. If you want to follow the coding, you need a laptop, and you also need a Google account. We are going to use Google Colab and some basic understanding of Python. We are not going to use C and C+ before today because, but you can continue if you understand C and C++. Feel free to ask questions online, and we are able to answer a question, I think, anytime. So today I'm going to introduce a little bit about GPU programming, and after the history, we are going to talk about Cuda. Cuda is a library designed by NVIDIA, and it's right now a very popular framework for GPU programming. And we are also to use Numpy. Numpy is a wrapper, Python wrapper. above Cuda. So if you want to do Python on GPU programming, Numpy is one of the options we can use. We are going to go through two examples. One is about a bandwidth example. Bandwidth is a very important concept in parallel programming. And we are going to go through another real example, which is a molecular similarity searching. And finally, we can summarize and have more discussion on the. Okay, let's move on. The GPU, first, it was designed and created for graphics. So it's mainly for applications from gaming or design. So one of the application they need is the technique of ray tracing. So here I show some algorithm of a ray tracing. It is, to simplify, there is an algorithm for each pixel. And actually, each pixel has different data, but the algorithm is totally the same. So this is a natural question which needs a solution of parallelism. In the right, you can see a picture of ray tracing. This is a little bit even complicated before, even complicated, because there is a recursive ray tracing process to generate this kind of image. Okay, so bandwidth. So bandwidth and we always heard bandwidth or throughput when we talk about GPU or actually, this is a concept from telecommunication, but it's very important. We can go through an example to understand. For example, we need to process an image, which is 640 multiply 480 pixels, and suppose we have 4 channels for colors. And if we need to generate an animation, for example, we have a frame rate of 30 frames per second. So the question is, what's the requirement for bandwidth for this task? We are going to go through the by coding. So this is the conditions we have. We have the image size, which is this, and then we have the channel for the colors, and then we have the FPS. It is the frames per second. Let's put 30. Before we start the coding, I need to mention one thing. If you want to use GPU in Colab environment, you need to set here the runtime, click the runtime, change runtime type here. You need to choose hardware accessor here, you choose GPU. Otherwise, there will be no support from GPU. So we save the setting here, and if you can also change the editor settings here. For me, I like Vim, so I change Vim.
Me too, I love Vim.
Yeah. So, okay, so we have the condition here.
Yeah. Let me just double check. So
Yeah.
I'm following along.
Okay.
So when they change the runtime to GPU,
Yes.
I'm saying please use a GPU instead of a CPU, right?
Yeah. Yeah.
That's it?
Yeah. Right now, the example is doesn't require GPU, but later on we will need GPU. So if you change later I'm not sure. Maybe you'll need to restart
I
the
see.
notebook again from zero. So let's do it from the beginning.
Okay, cool.
Okay, let's move on for the example. Actually, we need another parameters, which is the size of the we are going to use a 4-byte float to represent the data. So we need these parameters too. So let's do the calculation. We can run here. So we are going to calculate the data size of, maybe I just copy, which will be
So
yeah.
from my understanding of GPUs and things like that is the size of the data is
Yeah.
really, really important. So
Yeah, that's true.
yeah, so I think when you're doing some normal programming just on the CPU, if you're dealing with like one number, two numbers, you don't care so much if that one number takes up 32 bits, 64 bits, 128 bits, because it's nothing compared to your main memory.
Yeah.
But on GPU, everything's got to line up. If you've got thousands and millions of numbers, double the size is much, much bigger.
Yeah, that's true. We for parallel programming or for GPU programming, that's why it's so popular for data science, because we always worry about the big volume of the data. Okay, let's continue on the example. We have data size per pixel, which will be channels plus size of float. Okay, so this is the data size for each channel. We have 4 channels and 4 bytes for each pixel, and we will have data size of the image, which will be image size plus multiply data size per pixel. Okay, so we are going to print our result, data size of an image, which is data size of image right.
Okay.
And we are going to calculate the bandwidth here. Bandwidth in theory will be data size of image. So the bandwidth, actually the unit will be bytes per second. So it will be, the formula will be the data volume divided by the time we are going to use to process this data. So the time will be the reverse of the FPS, right?
Okay, the inverse of FPS is that's how long one frame takes, right?
Yeah, that's right. Good. And the unit will be byte per second. So the result will be bandwidth required bandwidth. Yes. Let's use Mega. Okay. Let's see the result. Okay. So the data size of the image will be around 5 megabytes, and the bandwidth required if we want to generate an animation at a speed of 30 frames per second. The bandwidth required is around 150 megabytes per second. So this is in theory.
Yeah, and maybe just for people who are watching and following along, and here we've got some, if you've not seen it before, this is a Python F string, and the bit after the data size of image slash and the colon there is just to format the number nicely in megabytes instead of having a big number of bits. So maybe some people haven't seen that.
Okay, thank you. So here we have the theory, and right now we go to the reality. We are going to see what's the CPU in the Colab environment will do for bandwidth. So let's do this. We are going to go through the realities with CPU on Colab. Okay, so we are going to have the count of float data in data. It will be channels multiply image size. And let's create some real data. Let's just create a 1, 2, 3 this kind of a sequence for I in range count. So we have created the data we are going to process. Let's just show the first 10. So it will be 0, 1. It's a sequence data. And the size of data, we are going to do size of data will equal to count of data multiply size of the size of a float. And we are going to use some timer. We are going to use a library timeit. So this will record the duration we are going to require for this task, and we continue is start timer, and we are going to define some simple task for the CPU. We're going to use so let's define the task for this data will be let's get the square root of the data and then add the square root to the data to itself. And we are going to have the duration when the CPU finished the task. So actually here, this kind of operation we are simulate, for example, to process an image, and you can define any operation as you want. You can just +1, the simple, or even very complicated process. So we are going to see the result here. Print. The duration. We will show the duration, and then we will calculate the bandwidth again. Bandwidth CPU size of data.
So before we calculated the kind of theoretical what we need bandwidth to do this sort of image processing at this speed. And now we're looking at how long the CPU takes to actually do some of these calculations.
Yeah, that's true.
And seeing how much bandwidth we get just using the CPU.
Yeah, let's see how much bandwidth we can get from the CPU.
Okay.
Make a guess. Whoa.
I don't know.
So here we have the results.
Okay.
We have the duration for this kind of operation is 0.4 seconds. So the bandwidth falls down to 12 megabytes per second.
Yeah, I got almost the same result. Exactly.
Yeah. And so this is let's stop the coding a little bit here and go back to the presentation. So we answer these two questions here. I hope you have a basic concept of the bandwidth right now. We continue to the next slide. Yeah, we finished this part. So we can always see a bandwidth or throughput in a GPU specification. As you can see, for the normally here are some parameters I extract from a specification of NVIDIA product A100. So we can see the process capability. They have 90.5 teraflops. This is the operation they can do in 1 second of the processor. So it's a concept of bandwidth, and they have the memory size and also memory bandwidth. It is 1.555 gigabytes per second. This means how much data the memory can send, or the CPU or the processor how fast it can get the data from the memory. And here are some other very important parameters. For example, the power. GPU is another new device, and it requires more extra power. So when you decide to, maybe you want to you upgrade your desktop with a new GPU, you need to take care, maybe you need to change the power supply too. And there's another specification, which is compute capability. This is for A100 is 8.0. This kind of parameters always you can see very often in hint messages from the NVIDIA programming toolset. So we will talk about this later too. So for me, it's the same. For many programmers, when they heard about a parallelism, there's always another concept, which is concurrency. Sometimes at the beginning, we mixed these two kind of concepts. So let's make it clear here. So parallelism, the purpose of parallelism is to improve the throughput. As we did before, we can see for parallelism, we always need higher bandwidth, large data volume. This is our purpose. But for concurrency, the purpose is to improve efficiency of the processor, to decrease the response time. So the mechanism behind parallelism, we have the same type of task, and these tasks are performed simultaneously in the same time. And for concurrency, the task could be different types. It could be your send a request through network, also it could be some computation in the processor, and it also could be you read data from your hard disk. All these kind of different tasks. So the mechanism, what we do is we organize these all different tasks in a proper way to make the processor do not be idling for a long time. So the keyword for parallelism, it will be always multiple processor. We have maybe new hardware. For example, Google has a new hardware which is TPU. It's not very popular, but it's purpose for parallelism. And we have a large number of tasks, as we talked, and the bandwidth, the throughput. And the keyword for concurrency, normally it's for a single processor and different type of task. And for one processor, we need to process different tasks, so we always switching between these tasks. Since right now, the CPU always have multi-cores, we have 4 cores or 8 cores, so the programming on the CPU environment, it could always be a mix of parallelism and concurrency. It's a mix of these two concepts, but we need to, it's better to be clear of these two. So if you have the concept clear, it will be better for the design of your programming, for the architecture of your program. Okay, let's move on. There is some, we are going to do some improvement of because right now the bandwidth is much lower. There is maybe two improvement we are going to do, because one is the Python is an interpreted programming language, so it is not compiled in time. So this could be could take longer duration, and thus therefore decrease the bandwidth. And there are also another improvement, which is the data type. So let's see what we can do. Okay. We are going to add another new code here. So we are going to do just in time of Python. We are going to use the library we just talked before, the number. So we are going to do import number here. number, what they do, they will compile the Python code and it will run just like the speed of a C or C++ program. So let's define the JIT square root function. This is the operation just as before, but we add a decorator to make it compound when running. We're going to return the data here. And maybe we can copy the this code.
We're going to use the same timer. Right?
Yeah.
Which bit did you copy?
Yeah.
I'm just trying to make sure I'm copying the same part. I just got lost.
Copy cell, copy selection.
Okay, just the part from the timer. Okay.
Yeah.
So we're copying
the
part with the timer and the displaying the information.
Paste. Maybe we can let's go through typing maybe.
Yeah, okay.
We have the count of raw data. This is like before. Channels multiply by image size. And we are going to use another library, which is Numpy, We are going to use the function from Numpy to generate the same kind of data as before. Let's define the type of data, which will be, and the size of data, count of float in data, multiply by float. Yes. Okay, so let's show the first. Okay. Let's see what's happened to this data.
Okay, so
there's an arrow, tap arrow here.
Print.
And yeah, let's do some copy arrows here.
Or just show the last bit of your code and explain it one more time.
Yeah, and then we copy the last two lines. It will be the same. Okay. Okay.
So
There is an arrow here. So we are going to, let me explain the code here. We import two new library, which is number and the Numpy. Number will do just-in-time compilation for Python. So we redefine our operation for the task here. And here, this is the same count of, we generate our data through a Numpy. And we just check the first 10 elements of this data. And we start to record the time, how much time they required for this operation. And then we do the task here. And then we stop the timer.
So the number is doing just-in-time compilation.
Yeah.
Why do we need to use Numpy?
Numpy, actually, this is because they are combined with Numpy JIT. So when you use this kind of decorator, so the data has to be the type from Numpy. Okay. Let's go check the result. Yeah. Now we have result here. We can see the result before and after, and the time is a little bit shorter. It's a small improvement. It's from 14 megabytes per second to 18. Okay, so this is what we can do. Actually, we can run again. If you run again, it's better. It's doubled.
Why? What did you change just now?
I did not change. I did not change anything. You just run the second time.
Why is it faster the second time?
This is maybe something in below inside the library maybe. And I imagine maybe there is something because of the collaboratory environment, because it is a doc image. Maybe they optimize the task you're going to perform. So this is something we don't know. But actually, for this for GPU programming, there's always a warm-up. Sometimes there's always a warm-up for maybe they, for example, the hardware they put it in idle status, so to save energy, something like this. So make sure you do a warm-up and then perform your actions, your really actions after that. Okay, so this is we improved the code through just-in-time compilation, and we changed data type. So this is what we do. And the next, let's do since we have a parallel CPU, so we can do a parallelism with CPU. Let's try what we can reach of the bandwidth for with CPU. So we are going to use another number features, which is vectorize. And we define our operation like this. So we are trying to do parallelism with a CPU. The function we are going to feature we are going to use is the vectorize decorator from number. So we are going to copy just copy this code, I think. And now we change the let's add a CPU. So let's see how we can.
So you copied the same version from before.
Yes.
And now we're going to use
We changed
CPU vectorized
the version
and that's
of
the only
the
difference.
square root. Yes. Let's see what we can reach. Ooh, it's a little bit better than before. It's around 80 megabytes right now.
Nice.
Change, but whoa. In average, it's 80.
Okay.
Okay. So let's move back. Shall we take a little break here, maybe?
Yeah, okay.
It's already
so we've been going for about
minutes.
45 minutes. Take a quick break. If there's any other questions on the YouTube live, put a question in the chat box. We'll take a couple of minute break and then we'll get back to the next part of the class.
Thank you.
Okay, coming back from the break. Let's get going again. Dive into part 2 with some GPU programming.
Yes. So we have some basic understanding of the parallelism programming, and we do some experiments on bandwidth with CPU and some simple data processing. Let's talk a little bit about the GPU history of GPU programming. So I would like to say for the programming model of GPU, it's becoming more and more open, because at first time it was designed only for graphic applications. So they use fixed functions, and later on they use shaders. This kind of programming is like you set some parameters and you get the result. And right now it is much more open. It is open API for not only for the graphic, but also for general purpose processing. And the suppliers, they issue these kind of programming tools. For example, we have NVIDIA, which is right now the dominant player in this market. They issue Cuda in June 2007, which is much earlier than the others. And they have a great documents and the official tutorials. If you want to learn by yourself, these are really great. You can follow the official ones. And I just learned that AMD is doing the same thing. They issue an ROCm platform on 2016, much later than NVIDIA, because they want to maybe they want to catch up. And there are also options. You can programming on GPU on other open directives such as OpenMP and OpenCL. But for my personal experience, since GPU programming is always related to the hardware, so you need something I would like to say native from the supplier. Maybe it's better. And why? There's another question: is why GPU programming is becoming so popular right now? I would like to say it is the revival of the neural networks. It is what we call right now the AI era, the machine learning. There's many great progress in this field, but I would like to mention one, which is AlexNet, which happened in 2012. It is a fast GPU implementation of convolution neural network written based on Cuda. As you can see, AlexNet, it won the competition of ImageNet in that year, and it is the first time to bring the error rate below 20%. So it's really a milestone for this field. And there's another incentive which push the data processing market. I would like to say is the cryptocurrency Bitcoins things. So you can see the market is in exponential growth right now. So Cuda, we mentioned a lot for Cuda. Cuda is a programming platform from NVIDIA for their hardware, because NVIDIA is only provide GPU. And so as you can see, Cuda is based on these hardwares. We mentioned the compute capability before. It is actually different numbers corresponds to different hardware architecture. There's always new features for the new architecture. So sometimes you need to be aware of what you have in your hardware and which is the version of your Cuda they match or not. Some features can be used or not. And on top of that, you can programming in C and C++, which is native for Cuda. And also, you can also programming in Fortran. Fortran is, I would like to say, it's for people from scientific computing community. From my personal experience, Fortran, you can do it. Right now, there's only one thing you need to be aware is if you want to do Cuda Fortran on the Windows, they are still working on the compiler right now. And for the others, they're totally fine. And the Java Python wrapper, just like we did today, we are using Python wrapper and the others. And they built other libraries too. For example, cuDNN and the TensorRT. This is for machine learning. And also here we have cuFFT, cuBLAS, cuSPAS. This is for matrix and the faster Fourier transform for signal processing and for matrix operations, and all other libraries. You can use it directly. It's save just like some mathematical libraries. So let's start our first contact with our GPU, with the GPU programming. So it's very good. We have GPU support from Colab environment. So first time maybe we can check what we have from this environment. We just import Cuda from Numpy, and Cuda, there is a function Cuda detect to find out what we have hardware. Oh, so we find one Cuda device, which is Tesla T4, which is NVIDIA product. They have compute capability 7.5, which is old architecture. And
Can I
yeah.
ask a question?
Yeah.
So I did the same command on my Google Colab.
Yeah.
And I got a Tesla K80.
Whoa.
So it says compute capability 3.7.
3.7.
So is it just
3.7?
3.7?
Really?
Yeah.
It's a little bit.
Is it just like random what Google gives you on Google Colab, or how does that work?
I think they actually for this environment you definitely have has a shared resources. They use maybe some Docker or Kubernetes environment. So when you open it, you share part of the resources, and these resources are allocated by random, I think. Yeah.
Okay, so we might get different devices depending on when we're doing it, or how busy it is, or maybe how much we pay.
Yeah, there is a pro version,
Yeah.
of course.
Okay, cool.
And let's move on. Let's do parallelism with CPU right now. So the simple parallelism will be, we still use the vectorize decorator, but we specify a little bit here. We use we add more parameters in the decorator. So you can see we have a float 32. So this is the returned type from the function. And this is float 32.2. This is the argument of the function. So I will finish the function and then go back to these parameters. Let's do GPU and then return. These are the same. So here, these are the arguments of the function. And if you, here we have only one argument. If you have two, so you will add something like this and something like this. And there is an arrow here. There's no need to put. So just like before, we copy almost the same code here from this line. Oops. We copy paste this.
Okay, so we're going to be doing the same thing as before.
For the remaining parts, I
using
think.
the GPU square root.
Yes, and we remember to change here the function.
Yeah, maybe bandwidth with GPU is what you might want to put on your output.
Yeah, that's true.
Tidy that up.
Yeah. So here we go. We got very low bandwidth for the first time, and then we do a second time. Still not.
Okay, I got a similar
similar result.
Yeah.
It's around 30 megabytes. So you might ask why.
Yeah, I'm thinking, why?
Why its GPU is not as fast as we expected? We will go back. We will go back to the presentation and answer this question later. So we have an open question here. So why? Because for this kind of new devices, there's always some overhead of the data transferring. So let's see what a CUDA process it is. Actually, they said it is a heterogeneous programming, which means we combine the code of CPU and the code of GPU together. So the process flow of CUDA, which typically is we have the data in our main memory, and the CPU is coordinating all the tasks, and you copy. First of all, we copy the data from the main memory, the memory on just normal memory, to the memory of GPU, and we perform our task on GPU, and we send back the memory. So we can answer from this slide. We can answer the question: if the time stay here is not long enough, so the main bottleneck will be the duration of transfer the data from memory. So that's why we can only reach 30 megabytes per second, because our calculation is very simple. It's compared to the data transfer time, it's minor. Very it can be ignored. So this is the heterogeneous programming. Actually, if we go deeper to number vectorize, we have some concepts. You might read a lot of these very important concepts for the GPU programming. First is kernel. kernel, we always heard Cuda kernel. Kernel is the code which are going to be executed on GPU cores. So this is kernel. Thread could be it's a similar concept when we compare to the CPU programming. It is the task. Thread is correspond to the task. And the block grid is we would like to say it's the how we organize this thread. So a block can contain a number of threads, and a grid can contain a number of blocks. So it's different levels for the thread. Actually, this comes, I guess, this may come from the application of graphic is always 3D organization. So they put the thread in a 3D organization to process the pixel in the real world. And as you can see, a block contains a lot of threads, and a grid contains several blocks. And it also corresponds to the hardware too, because in the hardware, in a GPU, we have a Cuda core, and these cores are organized into a streaming multi-processor. It's a Cuda SM, and in one GPU, there are several SMs, so there are different levels. So in the software side, they create something correspond to the hardware. So we explain Cuda core and streaming multiprocessor too. So here we have some details about the SM streaming multiprocessor, as just I mentioned before. So there are several streaming multiprocessor in one GPU, and so remember there are several Cuda cores, normally hundreds of, and these Cuda cores, they share L1 level 1 cache. So different SMs, they have different L1 cache, and all these SMs, they share the same L2 cache, and then to the global memory. Here, the global memory is the GPU memory. But sometimes you need to be careful about the architecture, because I think this is the latest architecture, but for some old architectures, this could be maybe L2 is shared only by the SM itself. It could be different. And this is an old GPU, which is a Pascal. The architecture is Pascal GP100. So for this, they had 64 Cuda cores for each streaming multiprocessor, and for the whole GPU, they have 56 streaming multiprocessor. So in total, they have 3,484 Cuda cores. So a big number of. As we mentioned before, we have a thread, block, grid. So if you want to do something, not only something even below the number vectorize, you are going to use these features. You are going to use the thread IDX, block IDX. Here is the example of to increase the element by 1, as you can see. Yeah. Okay, so let's go through the coding again. So this time we make things a little bit complex than before. We do a comparison vs GPU. So we copy the function. We copy the function here. So this is for CPU, and we also copy the function here. Okay. We add another parameters because we want to make our processing a little bit heavier than before. So we add another loops. We just do it multiple times to make the data processing a little bit heavier. And here we add for the GPU too. Remember, we mentioned we need to declare exactly the type we need, and we can copy paste this part. Yes. And we define a new run function because we want to try different parameters for the loops. We are going to the function for CPU and the function for GPU and the loops. So for each, we are going to a similar things before. Kernel's image size data Numpy range count of floating data type equals Numpy and the size of data equals count of rows multiply size of rows. And you need to do a little bit special things for the GPU. We are going to make the second argument for the GPU function, make an array for that. So remember, for GPU, they are always handling with arrays, with list. So we start our timer here. The data for CPU, we are going to oops. Bandwidth for CPU will be size of data divided by duration. Yes. And the print CPU first. And element after. The data. Okay, this is for the CPU part, and we can copy this for GPU. I suppose I changed. That's why I feel different. So let's anyway, we need to change all the C to G.
I have a quick question.
Yeah.
So we've got, oh no, I've realized my mistake.
Yeah.
So we're doing basically the same thing for the CPU version and the GPU version.
Yes.
Here, doing the counting.
Yeah.
Checking that.
We make a comparison about these two, and we print out the times. Duration together. And for CPU and the GPU respectively. Okay. So we print the duration for CPU and the GPU to show their difference directly. And the bandwidth to see bandwidth. Let's show in megabytes. So this is the ending for loops, and we print line break to separate. So we are going to perform on different level of computation. Let's do for once. This is what we did before. And let's do for 10 times. Let's do for, yeah, sorry, error, 10 times, 100 of times, 1,000 of times. So we are going to run our functions like this. For loops computation, good to run the CPU and the GPU. Be careful. Here is CPU, GPU. The GPU data processing, and then loops. So let's do a warm-up before the loops. Okay, let's see what we can get.
Okay, so I think I managed to keep up. See if there's any typos. Maybe one.
Okay.
Yeah, if anyone's following along right now, try and
Okay.
type an int. Oh, hang on. So what? So
yeah,
mine. I think I've made a mistake somewhere, but mine seems to get slower. With the bandwidth seems to go down for the higher number of loops.
Yeah, that's true.
Oh, is that normal?
That's
So
normal.
what did you get for 100 loops?
For 100 loops,
yeah.
we have we have 9.6 for the CPU, and we have 600 for the GPU.
Well, I'm getting about 2 for both.
2 for
I think
both.
there's a bug in my code. Let me
Okay.
bandwidth duration. Okay. G data, C data, C duration. So a bit of bug fixing. That looks better. I'm just fixing the bugs in my code.
Yeah, continue.
Okay, this looks more correct.
Looks
I think
better.
But maybe my GPU speed is not as fast as yours.
Yeah.
Perhaps because I've not got as good hardware.
Okay.
But I think I got up to about 160 megabits
for which loop?
For 100 loops.
For 100 loops. Okay, 100. So for here, in my notebook, I have 600. So let's go through the results from the first line. So this part is the warm-up.
Yep.
And this is the real part. Well, you can see the CPU has a really high bandwidth, right? They have for me, it's 2,600. And you?
Mine is 430.
400, even higher. And so for simple, you can see for simple calculation, you don't need a GPU because you don't need to send a lot of data between memories.
Exactly.
And if we are a little bit make the computation a little bit heavier, the CPU slows down quickly. For the second, I have 219. How about you?
So when we go down, so the CPU is 63 and the GPU is 92.
63.
Mm.
For loops 10?
Yeah.
Wow, okay.
I don't know what, I'm just going to double check my code. I think it's correct though.
Okay. So from my side, I have the around 300 for CPU and 700 for GPU.
Mm. For that one I got, oh, that's strange. I got
Mhm.
2 for CPU, 160 for GPU.
160.
Oh. I'm not sure what's going on.
Did you have a warm-up?
Yeah, I put in the warm-up.
Mm-hmm.
Maybe run it again and see what happens.
Maybe you run again?
Kind of similar numbers.
Okay, maybe it's related to the hardware.
Okay.
So if we continue for the loops 100, you can see the CPU continues to slow down, and the GPU keep its speed. And for the 1000, the CPU is really slow. They need 6 seconds, and still for the GPU we need only 0.02 seconds. So I'm going to challenge a little bit more on the GPU. So I'm going to add 10,000 here. Let's see what we can do on GPU. What is the limit of a GPU?
Can you just show me,
Yeah.
when you've finished that, can you show me the beginning of your run function just one more time?
Okay, I finished this line. I will go through from the beginning. I will add 3 more parameters for the loops. And let's go from the beginning. So this is for run.
Okay, so doing the calculation, float, I can't float the data.
MP loop.
Yeah.
And we add a little bit things here because CPU is really slow. We don't need to see his result, and we need to wait a little bit long. So we put, if it's we know for 1000 they need 6 seconds, so just finish on 100. If it's slower than that, let CPU do its work. And otherwise, we just give a 0. Okay, so we add a little bit modification to the CPU work part. We continue to checking the code. The GPU part is similar to the CPU part, and this is output. So are we ready to run?
Yeah, I think I've got it. And I think I found my bug as well.
Okay. Let's run.
Oh, nice.
Nice. We have checked. Last time we have checked to 1000. Let's see 10,000. As we can see, GPU becomes a little bit slower than before. It's slower down by, for me, it's slower down by 5 times.
Yeah, okay, so mine for 1,000 loops is about 177.
Yeah.
And for 10,000 it's about 30.
30, so 3 times. And if we continue for 100,000,
Yep.
mine is slowed down to 12.
Yeah, on 100,000. Yeah, mine's down to about 4.
4,
megabits.
okay. So, and for 1 million, it slowed down to 1.
Oh,
For me, it's
I didn't even do it for 1 million.
Okay.
I'll add it in now and see what happens.
Okay.
Oof, working. For 1 million, the duration is about 10 seconds.
10 seconds.
So it's
Okay.
about 0.5 megabits per second.
Okay. Mine is 3 seconds. So I think the hardware is different for for different users if you log in different time. So this is the comparison part. So we understand that maybe to use which kind of hardware, it totally depends on your application.
Yeah, I think it was nice to see today how, in some ways, the GPU programming was a bit easier than I thought. Like, as long as I've got the data in arrays and vectorized, I can use some of these decorators and just think about it a little bit and get all that power of a GPU.
Yeah, I think they these rappers, they really did a good job to make something complex things simpler. Yeah. So I think it's time, right?
Yeah, I think that's a good time to finish.
So what I suggest, I go through quickly the remaining slides and let's see. Okay.
Yeah.
So
okay. Just take a look at what's left and maybe what might happen next time.
Yeah. So what we are supposed to do, we are going to go through a final project of a molecule similarity search. So for a molecule, it's a graph. So if you want to do it on GPU, you have to vectorize this. So you need to a representation. So normally people in this field, they use a fingerprint, which means they hash the substructure of the molecule into bits. So there's a algorithm to calculate the similarity coefficient. So here is the formula. And for the data, we need the data of molecules. So you can download the data from Canva, which is, I think it's NBO for how to say it, they offer free open data source of molecules and even biology data too. And to generate the fingerprint, you need some cheminformatic libraries. So I suggest RDKit. Here are the example codes. You can generate a fingerprint from molecules from molecules. So you can do it by yourself. I will provide all the materials, and I think I will provide the basic code to start these projects online, and you can work on top of that.
Yeah, I think maybe what we should do is share the notebook that we used today.
Yeah.
And then people can compare what they've got with what we wrote.
Yeah.
And maybe in a future event, we might do this kind of chemical stuff as well.
Okay.
Because I think it might be a little bit more complicated than what we did today.
Okay.
So it might take a bit of time.
Yeah,
but,
that's a good suggestion. Okay, let's keep for the next time. So a quick summarize of today. We talk mainly about bandwidth today. So I think it's, in my opinion, it's an important factor of parallel computing, parallel programming. And we talk about the difference of parallelism and the concurrency. So you need to be careful about data transfer between devices, and you choose the best. Any technology, there are many options. You choose the best fit for your applications. And here the last thing is for the next time. when we finish final projects, there are other improvements on the result too. So that's all for today, I think.
Excellent. Yeah, I think, thank you so much for your really easy to follow and easy to understand talk. I'm really excited for the next time.
Thank you.
Yeah, so, and thanks everyone for watching online. See you next time. Bye-bye.
Thank you. Bye-bye.